Good evening. Welcome to the special physics colloquium by Professor Arif Babul, distinguished professor from University of Victoria. He has several other affiliations. Currently, he is an Infosys professor in physics at IISc. He is also at Leverhulme visiting professor, University of Edinburgh. So Professor Babul is visiting IIT Tirupati, and he was very kind enough to accept our invitation to also visit Isaac Tirupati and give a talk over here. So he has had a long day today, I think. He has special seminar in the morning, interacted with the students for an interview for their college magazine or ISER magazine, and now we have the special colloquium by him. It will be followed by an interaction session with the Celestic, the astronomy club of the at ISER Tirupati. So without further delay, I would request Professor Babul to give the special colloquium today, which would be on supercomputing the universe.
Can you hear me? All right. Thank you very much. Yes, it's been a bit of a long day. I'll just sleep well tonight. But I've actually enjoyed myself immensely. I'm always thrilled to come across students who are passionate and curious and engaged. And like university professor, nothing pleases me and delights me more to see that the future is in safe hands. All right, with that, let me start on my talk. The title, as you can see there, is Supercomputing the Universe. And sure enough, yeah. I think I'm having that. So can you come up and
No, it's fine.
I need to go back, right? So share and that and share. Yes, okay, thank you. Our line of my talk is as follows. I will give you a contemporary history of cosmology and large-scale structure, which is what we will be talking about today. I will identify and how we go about modeling the physics of cosmic structure formation. And then I will talk about how much progress in the last couple of decades. And also, I think it's very important to highlight challenges we face, because challenges are interesting for you. If you're just starting out in the field, this is where you have the opportunity to make your mark. So let's get started. In just around 3 decades, our understanding of the cosmos has literally improved in leaps and bounds. 3 decades ago, the physics understanding was highly uncertain. For example, the age of the universe was estimated to be anywhere between 7 and 20 gigayears. So just think about it, right? That's more than 100% uncertainty. We knew that the baryons, ordinary matter that makes us up, that makes the Earth, that makes the stars, anything that we see in the universe, ordinary matter, only a minor component, ranging from anywhere between 5 and 15. The model of everything, including the large-scale structure, expansion of the universe, were highly imaginative, but largely untested. And they were very simplified models. What was the state of affairs when I was starting graduate school? Things changed dramatically in the 1990s. And the factors that really triggered this change were twofold. One, you had the development of CCDs. Prior to that, telescopes were taking images of the sky using film. Then you had to develop these plates, size it, and it was a lot of work. But at AT&T in New Jersey, um, condensed matter physicists had developed charge coupled devices with efficiencies of something of order, if I remember correct, it was about 50%, kind of bad, not enough to make it useful to anybody. This was an era when companies like Xerox and AT&T had physicists and astrophysicists sitting in the companies. So the companies making making devices that were supposed to earn them money. A group of scientists who just worked on blue sky projects, and were one of them. So you know that Penzias and Wilson, who discovered the microwave background, actually worked at Bell Labs. And in similar sense, when the CCD cameras were developed, people at Bell Labs, astronomers, and said, you guys are always looking for digital ways of taking of the sky. Here, take this and see if you can figure it out. And sure enough, astrophysicists, engineers working together literally changed the efficiency going from 50% to. By this time, the devices had been loaded onto the back ends of the telescopes. We were getting images that were digital. You could analyze them right off when you collect the data of the telescopes. So that transformed how we were. At the same time, computing exploded. We went from desktop computers to convex supercomputers, and the sky at that time seemed unlimited in the sense. And for us, graduate students who were just starting out, this represented an opportunity. Why? Because first of all, the universe is extremely complex. There are thousands of physical processes that are happening, and they interact with each other. And the physical processes come from virtually every domain of physics, except quantum mechanics. Not even quantum mechanics enters into the picture when you talk about radiative processes, collisional interactions, and things like that. So every domain of physics was contributing interactions. Even chemistry was contributing because we had chemical reactions in extreme environments taking place, leading from elements to molecules, molecules to complex molecules, to methane and ammonia and all these gases that were discovered in outer space. So we had these complex situations. We could do is build simple models. For the first time, we could actually take all these models, write up a code that included all of them, put it onto a computer, and actually hope to finish the code to finish running before your time as a graduate student ran out. So speed had improved, the capacity of the computers had improved. And so we could start models of the universe that were incredibly realistic. And with time, they became even realistic. It gave rise to a whole area that is known as computational astrophysics today. Now, what have we learned? Well, what we learned is that galaxies come in a huge variety of shapes and sizes. What you can see here are a range of galaxies that look like our own Milky Way. They are flat, they resemble pizza pies, except that instead of dough, they're made up of stars. And they're rotating around the center of the galaxy. But every now and then they get perturbed, some instability happens, and you get these beautiful features starting to form. So you get spiral arms, you get Colloquium spirals, you get grand design spirals, a wide variety, and some of these things people here are trying to understand using machine learning. So this is a whole area. But if you look over here, you'll see that there is a different class of galaxies present here. These classes of galaxies actually look like giant bowls of stars. So they're spherical. And then they are down here, typically small. They are much more amorphous in shape, and they are, astronomers are terrible at nomenclature. Like, we just can't come up with creative names. These are called irregulars, right? Galaxies are the building cosmic structure. Now, if you work on planets, you may disagree with it. But what I do is look at the universe as a whole, and I look at the structure of the. For me, galaxies is the starting point. Anything smaller than a galaxy is stuff inside the galaxy and potentially not directly applicable to the larger systems. So my starting point is galaxies are the building blocks of cosmic structure. Image that comes from the 2-mass survey. The band running in the center is the. I wish I could take it out, but it's not easy to take it out. So it's there, nuisance. But the rest of the dots out there are not stars. The stars have been taken out of this image. And in this image, 1.64 million bright galaxies. I emphasize the word bright because as our telescopes become better and better, we can go fainter. And if we go faint enough, we think that the number of galaxies in the observable universe will approach 1 trillion. So we're looking at 1 trillion galaxies out in the sky, and how are they distributed in this giant volume that we're observing? Well, if you look at this picture, you'll see that the galaxies up here and the galaxy distribution down here and the galaxy distribution here and here tend to look similar. So the universe looks homogeneous and isotropic, right? This is the interesting thing. Look at the galaxy distribution as you slice it down into distance. What I mean by that is if I take a picture of this room and I don't have any references, then everybody will look like they're collapsed in one frame, right? And I won't be able to tell who's in the front and who's in the back. So if I get rid of the references around me, that's all I have. It's just everybody's square. The night sky is like that, but distances. And so I know who's in the first row, I know who's in the second row, and I know who's in the third row. I know that, in the first row, this area here is empty. There are no galaxies. And I know that there's a bunch of galaxies here, so there's a group that's sitting over there. If doing that, what we find is that galaxies, first of all, are organized in these long filaments that span hundreds of millions of light years. Secondly, if you look again at these pictures, you'll see that there are high concentrations, regions where filaments intersect. And when they intersect, you get these regions of dense concentrations of galaxies. Turns out that in this region, there are galaxies. So this is all of those images that I was showing you earlier collapsed together, except the color coding has been preserved, so you can see the features like the concentration and the chains of filaments that run across the sky. Yeah, okay, so I don't have that image. I'll just tell you the story here, that these concentrations can have anywhere from 4 to 3,000 galaxies. Gravitationally bound together, they are essentially whirling and gravitationally bound. They're not just transient. They're not coming together and disappearing. They're actually stuck. They're basically in orbit. Okay? These systems are known as groups and clusters of galaxies. And so we have empty regions like what we as I said, astronomers are known as the best wind nomenclature. These are just voids. They're empty regions, so they're voids. Okay, so they're void chains. There are clumps that are clusters and groups. The question is, okay, this is how it looks in the sky. What happens if I take just one slice? I take my telescope. I'm not going to look everywhere, which is what this image is, but I'm just going to take a slice like this. And in that slice, I'm going to figure out how far away each galaxy is and make a map. So it's what we would, in gravity, to call the pizza slice of the universe. You just sort of shoot out and take a pizza. And when you do that, this is what it looks like. Pizza slices here, 1, 2, 3. And you can look inside a pizza slice and you see it looks frothy. Filaments and bubbles, filaments and empty regions. So the universe out to at least 200 mega years, not mega parsecs. It's been a long day. Megaparsecs is inhomogeneous. It's only when you get very far away and you start smoothing about a huge region, then it starts to look smooth and homogeneous and isotropic. But up to a significant volume, it is essentially inhomogeneous. Now, this, it was impressive when it was discovered because we did not expect it. And I remember when the very first came out, I was in second year graduate school, and all the theorists were abuzz about this because how did the universe form into these features? Structures start to come about. This was the question. And as I mentioned, there are structures that are concentrations, and here are just some of the main features around us of these strong concentrations. This is the I was trying to search for. I forgot the order because I gave a talk yesterday and it was in a different order. This was the image I was looking for. This is each one of these concentrations would look something. There are anywhere from few to thousands of galaxies together, and they are whirling about. Now, this is everything I've told you are ordinary matter, matter that shines, matter that radiates, matter that's easy to observe. But I also told you at the beginning, the universe is not dominated by ordinary matter. It's dominated by something else. And what is this something else? Well, first, what we do know is that it responds to gravity. And for an astrophysicist, that's enough. There are people in this audience who are particle astrophysicists or high energy astrophysicists who worry about trying to figure out what dark matter really is. Good enough to know that it just responds to gravity. Now, what does that mean? It means this. So imagine I have mountain ranges, hills, high mountain peaks, and if you think about it, it is equivalent to ordinary matter being like a dusting of snow. So wherever the peak has a little bit of snow in it, we see it. But the bulk of the mountain, the rocks, like hills out here, because they are made of dark matter. So dark matter, we realize, the skeletal structure of the universe. Within this skeletal structure, the baryonic matter is organized into galaxies and clusters, and we look and we see the galaxies and clusters, and we see the chains, but underlying of galaxies that I showed you are much more well-defined of dark matter. And this is one way to think about it, that the galaxy distribution is only showing us the tip of the iceberg, if you will, or the mountain specifically, and only the very high mountains where there is snow. The rest of the mountain is visible to us. And it sort of resembles this cartoon image. The galaxy is sitting in the center. That's where all the stars are. You can just barely make out the spiral feet. Then surrounding that galaxy, extending out almost a factor of 10 in radius further out from the edge of the galaxy, is a dark matter sphere that is enveloping and containing this galaxy. Within this dark matter sphere, there are many galaxies that are moving around, trapped by the gravity of this object. But the simplest picture is a single galaxy at the center and the baryon and the dark matter all around. Okay. So far, I've been talking about galaxy distribution, been talking about a single galaxy and dark matter. There is one other bit of information that I would like to share. is that the telescopes themselves, which we use to study the sky, are in fact or can be very much thought of as time machines. Why? Because light has a finite amount of time to travel. It has a finite speed, and therefore it takes a finite amount of distance. So the light from the sun, how long does it take to get to us? Yeah, 8 1/3 minutes. So that means that you're looking back at the sun. When you look up in the sky, the image of the sun you're seeing is not the image of the sun is. You're seeing the sun as it was. If the sun was to blow up, we would not know about it till 8 1/3 minutes later. The same way, galaxies are much further away than our sun, and therefore light takes millions and billions of years to get to us. So further away the galaxy, the further back in time we're looking. We're seeing the galaxy as it was billions ago. And in that way, you can think of the telescope as a time machine. And the furthest back we can see is literally the after the Big Bang. So when the universe was born, there was a tremendous amount of energy that was eventually transformed into radiation. And that radiation today surfuses the entire universe in microwave radiation, that you cook when you turn on your microwave ovens. And that radiation is something that we can detect as far back as 375,000 years after the Big Bang. So that's about 13.5 billion years back in time. So from here, it's 13.5 billion years and 375,000 years from the Big Bang itself. Now, we can detect that radiation. We can detect the way it looked all the way back there. And what do we learn from that? Well, what we learn is that the thing you do when you take this measurement is you see this pattern. It's sort of a yin-yang pattern. But the yin-yang pattern is mostly due to the fact that it's moving. This is Doppler shifting. Now, this is a physics colloquium, so I can say things like that and expect to figure it out or understand it. This is Doppler shift. Regions that I'm moving towards look hotter, and the regions I'm moving behind from look colder. You've heard motorcycles go by, right? Why? Well, as it's approaching you, the sound is getting compressed and you hear a higher pitch. As it travels away, you hear decreasing. Light behaves in the same way. If I throw photons at you, if I'm coming towards you, photons at 1 per second, you will catch those photons faster and faster and faster until I'm right in your face and I throw a photon. But when I leave, those photons will take longer and longer and longer to reach you. So you see this Doppler shifting happening, and this Doppler shift is this pattern. Where does this pattern come from? Well, the Earth is traveling around the sun. The sun is traveling in the galaxy. So it's orbiting the center of the galaxy. The galaxy is moving. Ultimately, you can take all that out. We know this. We can measure all these motions. We can take it out. When we take out all this local motion, this is motion due to our Earth and our sun moving around. When we take it out, we see patterns that look like this, fluctuations. Now, I have shown you different images there superposed because COBE was the very space telescope that went up and measured this. It measured these fluctuations, and the resolution was not the greatest, but you could detect the fluctuations. I want to just tell you one little thing about how amazing this result is. Take a lake. Imagine a very still day when there is nothing, not a wave, no ripples, nothing. It's just mirror smooth. Pull out your hair. Drop it on the lake surface. Now your hair is making a little bump. We can observe that little bump. 13.2 billion years back in time. And basically, this is what it is. The ripple that we can see, these fluctuations, are 1 part in 100,000. They are tiny little ripples, but we can see them and we can map. And that was the beginning. Before this happened, cosmology was known as quantitative theology. Our physics colleagues used to laugh at us because we were making up theories, very imaginative about it, but we were data starved. Beginning of a transformation for cosmology. We went from being data starved to now data rich to data overwhelmed. And this started the game, and I'll show you what happens. So 92, you have this sort of, but yeah, not so great image of the microwave background. Then in 2003, WMAP went up and took an image. Notice the resolution change. You are starting to see things in detail. And then you look at Planck, which went up in 2013, span of about 8 years, put out data that has resolution. And I haven't put up the next image, but there are ground-based telescopes now, South Pole, that are taking images at much higher resolution. And because of that, when I calculate the fluctuation spectrum, so I'm assuming many of you have already done Fourier transforms, right? And another wave and a smaller wave. I do the same thing. I take this map and I can effectively a Fourier transform, except it's a spherical analysis. So you're doing Legendre polynomials and things like that. But effectively, that's what you do. And I can calculate power spectrum. And what I get is these multiple peaks all the way down over 1,000 in scales, in wavelengths, if you will. And had predicted, based on the imaginative physics, what the microwave spectrum should look like before it was discovered. And I remember that there was a Russian scientist who was very famous, Zeldovich, who said, the physics is beautiful, but you will never see it. It's way too small. Today, I stand here showing you not just the first peak, but data has shown us all these little peaks, and these peaks together provide us with an incredible amount of information about the universe. So let's see if I have the slides. Sure, I do, yes. So let's see what we learned. This one is showing me what happens when I change the amount of matter in the universe, the total amount of matter. So I'm decreasing it and I'm increasing it. Notice as the amount of matter changes, the relative shape of the peaks changes. Peak could be bigger, could be smaller. The second peak could be bigger, it could be smaller. So a real spectrum based on this, I can fit the curve and tell you how much matter there is in the universe. This one is telling you this is total matter. This is telling you how much ordinary matter there is in the universe, stuff that we are made of, baryons. So you can see that as I change the amount of baryons, I can make the various peaks rise and fall. So if you give me the microwave background power spectrum, I can tell you lots of things. I can tell you how much total matter there is. I can tell you whether the geometry of the universe is flat or whether it's a curve. It looks like a horse's saddle with one curve this way and the other curve this way. What the shape of the universe is. I can tell you how much matter there is in the universe. I can tell you how fast it's expanding. I can tell you how much ordinary matter there is in the universe. So, as I said, we went from a model where we're more working out of physics, intuition, and imagination to being able to constrain these models using data. This is the end result, more or less. We can now do this down to roughly about 5% precision. And there's a telescope up there right now called the Euclid, and there's a ground-based telescope that just put out some interesting new results called the telescope, who are trying to push to a percent level precision and down to sub-percent level precision. So think about it. We went from 100% error, uncertainty just 30 years ago to now dreaming about sub-percent percent accuracy. Now, what do we learn? As I said, we know what the matter we know that the expansion rate of the universe is. We know how big those fluctuations are. We know what the age of the universe is. We can tell what the various compositions are of dark matter, of ordinary matter, heavy elements. We can figure out what the shape of the universe. This is where it gets interesting. Remember a few minutes ago, I told you most of the matter in the universe is dark matter. And I told you, I don't know what actually dark matter is, other than it is things that react to gravity. That's all I care about. It turns out that the geometry of the universe is flat, which means that there is something else. The number, flat universe, the number, omega total, if you will, has to be 1. Now, I can explain to you why that's the case, but that's a different story. Just accept it that if the flat, then omega total is constrained to be 1. If omega total is 1 and omega 3, what's making up the remaining 0.7? This is what dark energy is all about. And again, if you ask me, what is dark energy? I don't know. If you ask a physicist what is dark energy, chances are they too, if they're being say, I don't know. And we're all trying to scratch our head and figure it out. But we do properties of dark energy. It is like an anti-gravity feature. It causes the universe to expand faster. Gravity slows the universe down. So the universe is born, the universe is expanding, the gravity is slowing the universe down. It's like, when you are riding uphill, you coasting uphill. As you come racing off the track and start going up, bike slows down, slows down, slows down. Or you throw the ball up and same thing happens. Okay, that's what gravity does to the universe. It slows it down. Anti-gravity is like suddenly, it's expanding faster. It's like suddenly the hill turns over and you're now going downhill. And that's what the image is here. And so that's what we finding, that the dark energy is present at roughly 70%, and it causing the universe to expand. And then the deserts have thrown a wrench in that particular picture too. I won't talk about that because it's still kind of uncertain, and theorists like myself still don't know what to make of that result. But nonetheless, this is the picture as it stood before the results came out. Okay, so we have fluctuations. What are these fluctuations? It turns out that theoretical models of the universe expanding tell you that as you go back in time, smaller and smaller and smaller until finally it becomes so small that it's smaller than an electron. At that point, not just regular classical physics, general relativity physics, and all become relevant, but quantum mechanics becomes relevant. And so you get noise in the universe, quantum noise. But the universe is also born rapidly expanding. So as it rapidly expands, those fluctuations get stretched out. And they get stretched out so large that they cover the span of our observable universe and beyond. So these fluctuations are what you're observing here in the microwave background. They are actually created when the universe was tiny and continuously as the universe inflated and stretched. These fluctuations are important because it is these fluctuations that created the seeds for structure. Let me give you the simple physics problem. If I'm in a room that's absolutely uniform, everything is same in every direction, and so there's homogeneity and entropy. And I'm standing here. Which direction is the gravitational force going to be acting on me? Sorry? So, but what's the net? Right, net is zero. I'll be pulled equally in this direction as in this direction, as in this direction, as in this direction. I'm going nowhere. Net force on me is zero. These fluctuations, they break the isotropy. They break the homogeneity. If I'm a big fluctuation here, I will get pulled this way, and I will get incorporated. I hate to say this, but gravity and the dynamics of the universe is really capital. Why? Because the rich get richer. You start with a fluctuation, it just becomes a bigger and bigger fluctuation as it keeps accumulating everything around it. And a low density region, which was poor to start with, just becomes more poor. And, there's I'm a socialist at heart. I have to live with this. This is okay. These are the seeds of galaxies, clusters, everything that I showed you in the first part of the talk. The question is, how do you go from this to what I showed you earlier? Now, the problem starts. For a cosmologist, for a regular physicist, you have a theory, you have an experiment. You can go into a lab, you can repeat the experiment, change parameters, and you can do the experiment again. Or even if you have a large hadron collider, you can repeat the experiment 1,000 times, million times, collect data on statistics and everything else. We have only one universe. And nobody has endowed me with the capacity to press it again. So, how do I test my models? I told you at the beginning that when computers came around, one of the things that they endowed us with is with a capacity to build virtual model universes. And so this is what most people play as video games, been doing since 1980, except we've been doing it on the scale of the universe. And we do it over and over, and we test our physics, our physics. And so what does that mean? We want to go from that to this, go from that to this, protoclusters and clusters and large concentrations of dark matter and ordinary matter. And we want to go to a universe that is smooth but is frothy, like this. Question is, do we do it? And there's one other feature. We not explain the universe today. We also want to explain the universe as we moving over time. We can see the universe now all the way back to 300,000 years, 300 million years. And over that time, we can look at the universe slice by slice and figure out how the galaxies were evolving. I want my model to be able to capture that correctly. So that's the goal. And, as I said, we have one experiment. Now, this is a physics colloquium. So I see something here that I wouldn't normally say in a general colloquium. When you are trying to understand the universe, there's a scale that you must be able to study, the whole of the physics. What is the smallest physics that I want to understand? That's friction. So when I rub, my hand gets warm. That's a molecular viscosity. That's a viscosity effect that's due to atomic physics, right? Molecular physics, transformation of kinetic energy into heat. Now, that's the small. The biggest is I want to be able to capture the largest scales that how matter is falling into a galaxy and how the galaxy grows. When I take the ratio and I ask, how many orders of magnitude do I need to study? It's basically 30 orders of magnitude, or 10 to the 30 is what I want to capture. From the smallest to biggest, it's 10 to the 30. I can't do this on a supercomputer yet. The best in the world today can push it to 10 to the 9. So we have 20 orders of magnitude of physics where we still have to model and to the computer. The rest of it can do direct calculations, but 20 orders, I have to put in viscosity. I have to put in turbulence. I have to figure out how to model these things, to know the physics. So that is the basically we have a complex network of physical processes. They are non-linearly coupled to each other. They span an entire spectrum of physical processes. And we want to use numerical simulations. And you want to do direct calculations all the way through, but it's impossible. We can do some indirect calculations. Some we still have to be clever about it in terms of physics. Let's see. Yeah, that's what this particular image has been giving me problems forever now. All right, I will skip this, except for the fact, to start with the comment at the top, I can model dark matter only. I can take this, whatever it is, these particles, plunk them down, all the baryonic physics, all the complicated stuff, just allow for gravity. And I can figure out what happens. And what we find is that in a given region, small structures form first. Remember, my initial conditions is what the microwave background is telling me. And I have dark matter responding just to gravity. And I find that given region, small structures form first. Then these small structures merge together to form big. And in any given area, the most massive are the last to fully assemble. And how fast they assemble depends both on the law conditions and on the cosmology itself. Now, there we go. Is showing you a box with this dark matter laid out and initial conditions set down, and then you have gravity taking effect, and filaments starting to form, chains of galaxies, and you can see bright yellow dots are where the filaments intersect and where clusters are forming. So you can see the structures that we see before. And here is this is an old one. This is a simulation we did back in '97. This is a simulation that people in is it on? Okay. All right. So when I do that and I calculate the fluctuation spectrum in the mass function of structures that form in the dark matter, I find a curve that looks like this. Great, we can do that. But galaxies look like, you see, they don't look like the dark matter. Something is not right. And what's not right is that I haven't put in baryons. And the question is, will the baryons change everything? Well, if I put baryons in a very simple, I just throw the fraction of baryons in the dark matter halo, and I'd get the dotted line. But the dotted line doesn't look like what I see in the galaxies. So something more is happening. And so my challenge is to explain this. Starting with this, explain this. Similarly, if I look at the Milky Way-like object, and I ask, what is structures, things that are falling into the Milky Way dark matter halo? So the dark matter has clumps in it. And I ask, what is the spectrum of these clumps? There's the sort of the mass of the clumps, and as you get to smaller and smaller clumps, you see it's rising very, very steeply. So this is what you predict the clumpiness of the Milky Way should look like. This is what you see in satellite around the Milky Way. See, it doesn't look anything like that. So now the question is, what are we missing? And I told you, baryons, but just throwing in baryons by itself doesn't do anything. There's something more. Baryons are complicated. Baryons have all sorts of physics. So gas is collisional. It is described like fluid dynamics. Will undergo shocks. It'll undergo compressional heating. It suffers from turbulence. It has thermal conduction taking place. It has viscosity taking place. When the gas falls into a dark matter halo and is hot, it fills the entire halo. But after a while, it starts to cool. You are cooling. You are radiating right now in infrared. After a while, you'll get hungry because you've just lost a lot of energy. Similarly, gas is losing energy. As it loses energy, it loses pressure. If it loses pressure, remember, pressure goes as density times temperature. So if you lose pressure, you can't fight against gravity. So the gas will start to collapse to the center of the potential. There, it will collect, and if it becomes dense enough, it'll start to form stars. And that's galaxies in the centers of the dark matter halos. So gas cooling in the center, it leads to stars and black holes, and then you end with heating and cooling cycles. Why? Because stars, when they're born, eventually will die, go supernova, and they have huge explosions that drive energy in the surroundings. Similarly, radiate brightly. Sometimes they can radiate more than 100 stars. And that amount of energy that radiated out from a black hole, it's not the black holes are radiating, it is the gas around the black hole that's radiating as it's falling in. That gas, the amount of energy that you can extract enough to transform the environment around the galaxy, much less the galaxy itself. So we have all of this going on. You have stellar dynamics. Stars are orbiting around. You have black holes that are orbiting around. Black holes suffer dynamical friction, so they spiral into the center. You have feedback going on, so radiation and kinetic energy coming off from stars and supermassive black holes. Gas is being heated and ionized. It'll heat up, it'll get pushed out, it'll fall back in. It's almost like the galaxy is breathing, right? You push it out, the gas flowing in the center, the black hole sort of chokes, doesn't have enough fuel, stops, comes back in, and then you'll repeat. And so this cycle is continuously going, and we call that. In other words, the upshot of all this is that galaxy formation physics is complex, it's many component, and they're all related to each other. Each to another bit and affects everything else. And if you ask me, what can we do directly? Well, this stuff, gas and fluid mechanics, we can do this directly. Gas cooling, well, we can do it sort of, pretty much directly. But if you go beyond gas cooling and you look at stellar dynamics, some of it we can do directly, but some of it we have to do through model. Come up with a clever model to take care of the physics that's occurring on scales much smaller than what I can resolve in the simulations. And luckily, that kind of physics we understand, so our models are pretty good. I say that stars explode and supermassive black holes radiate and put out energy. There, unfortunately, we do not understand the physics well. And because we do not understand physics well, we have a model in our simulations, but in the back of our heads, if I was giving a colloquium in an astronomy seminar, I tell you how great our model is. The truth of the matter is, we are not sure. And keep this in the back of our heads. When we get our observers to test our models, we really are interested in how well we are doing here. So, and then there are other things like radiation transfer and magnetic field like that. For me, the biggest problem in our simulations right now, the greatest uncertainty is right here. I would like to understand how to do this better. Now, what do I get? This is an image from a simulation known as the Romulus simulation. What you're seeing is a time lapse image, you are seeing stars lighting up. So millions of years are passing very quickly, seeing the entire history of the universe unfold before you. You're seeing stars, you're seeing gas blowing up and lighting up. You're seeing galaxies turn on. These are these tiny jewels that are lighting up along these necklaces that are filaments in the universe itself. This is one picture, and I'm not going to belabor telling you a little bit about the simulation that we used. There is another simulation which I will end. When I finish, I'll stop, I'll turn on the simulation, and you can sit back and enjoy it. It's made by the TNG group. They have tons of people and tons of money, and so they've made an amazing movie. I wish I had that kind of resources, but I don't. I don't want to distract you from that because I want to get to the end of my talk, but I will show you the movie. You have to experience it. It's actually an IMAX movie. So the best thing would be to sit back and watch it unfold on a screen. Such is life. Okay, subgrid models. I told you that there are all these physics models that we have to put in to try and approximate things below the scale that I can resolve. Well, some of these have free parameters. Some of them don't because I understand the physics. Some of them don't understand the physics. I have to model it using some heuristic approach, phenomenological approach, and there are parameters that I need to address. And how do we take these parameters? What we do is we usually take two observed functions, usually stellar mass function today, and we tune those so that it comes out right. So here's an example of something that's coming out right in the Eagle simulation. This is the stellar density Eagle simulation. This is another simulation, TNG. You can see the blue curve here has been tuned to get it right. And this is another function like that that is done. So basically, we take two observables, distribution functions, and we try and get them right today in time. And the hope is that if I do that, when I run this thing, they come out right at an earlier time too. And I'll get all the other things for free. This is the galaxy stellar mass function going back 10 gigayears and then going back all the way to 13 gigayears. And you can see how it is basically matching. The green is the model, and the crosses are the data points. And you can see that the model and the data points are spot sort of frighteningly good given the things I mentioned, the things I worry about. All right, but it's quite remarkable. And then you ask me, why was the dark matter curve like this and the galaxy was like flat? That's because when I put baryons in the galaxy and they turn into stars, they start exploding. When they explode, they dry out. And so even if they had started like this in the first instance, as you and the galaxy gets starved of gas because you have driven away all the gas, it looks flat at the end. And the same is happening at the bright end. This is where the EGN, these black holes, are putting out energy and literally shutting down star. So we understand why the two ends of the galaxy mass function look the way they do. We tune it to something like this. And the amazing and impressive feature is that we can get the evolution of the galaxies going all the way back. Black holes. Black holes grow. In the present universe, we know that the amount of stars and the mass of the black hole is very tightly correlated. And so this becomes the test of our model. And so you can see these diamonds here are observations, and the blue result is the model that I've been showing you. This is showing how well it does. This was, so again, an impressive agreement with the data. This is highest resolution simulation, the one I showed you, the Romulus simulation. This is how the galaxies look like. Look at how the galaxies resemble the real galaxies. Elliptical galaxies, we have spiral galaxies, we have galaxies with rings, we have galaxies with beautiful spirals, and then we have galaxies that have flocculent spirals. So they are sort of not as pretty as these guys, but nonetheless impressive. You can get the structure right. And here you can see a galaxy that even has a warp to it. Edges are sort of turned up and down. So that's a warp galaxy. Probably had an interaction. This is another simulation, just like Romulus, which has comparable. And again, you can see the features that are in the galaxy. Bottom line, we can get the structure and we can get the dynamics of the galaxies pretty well. And we can the broad evolution going back in time, all the way back to 13 years back in time, pretty well. So I'm going to skip this. But choices still leave you with some differences. So here is a model. There are 4 different simulations. They all sort of do what I've just described. But now look at what happens beyond the galaxy. This is Simba. It's already starting to drive powerful hot jets from the black holes. In this case, it's happening so vigorously that the region around is already heating up quite a bit. That's what the red color is. This one is heating up too, but intensely as this, and these other 2 are not heating up in the same way. So what does that mean? That means that there is a way to test which of these models actually works. Maybe you can test, since I work with Simba models and I work with Romulus, I can actually ask the question, is the AGN feedback in Simba too powerful? Maybe I can fix it by having a better model. So how do I test that? Well, at IIT Tirupati, there is a new faculty member, Vikram, who's working with for about a year now before he arrived. And one of the things he does, region out here, this outside the galaxies, he looks at the gas and asks, is it hot? How hot is it? And is it as hot as this, or is it looks more like this? So that is one of the ways we can actually try and constrain our model. So as I said, in all due honesty, we are doing really, really, but there are still things to be fixed. And that is part of the fun of science, right? If the problem was solved, I could probably just retire at this point. But I have something to keep me going for. And that should be fun, because these kinds of problems will remain. Computers will only get faster. So for astrophysics, these differences are actually opportunities. Opportunity to even better our understanding of the physics of the universe. So let me give you the summary as it stands right now. Study of the cosmic structure has been transformed over the past 3 decades. Advances in the telescopes and computing. For most galaxies, the models that we have does extremely well at explaining the way they look and the way they evolve. We can also see some strains, as I showed, in terms of the AGN feedback. And want ultimately our models to be holistic. We also understand that the physics that happens inside the galaxies affects the larger environment. Interestingly enough, that larger environment then acts back on the galaxy. So you know this debate within nature versus nurture you have about raising children? Well, it turns out you have the same kind of debate in galaxies. It turns out that the answer here is that it's both true. The physics inside galaxies is the physics outside, that the way the environment gets shaped is also important. So and is just as important as the physics inside. And for model purposes, we have right. That's the important thing. And we're not quite there yet. This is the regime where the model needs to be improved and repeatedly stress test. And that's what we are doing. That's the challenge that we have taken on ourselves in order to improve models of the kind that I've been describing. Now, I'm going to, this is the end for me, but before you leave, just sit back, enjoy this. So, Hmm.
Hello. Yeah, I.
Oops, I should turn this off.
Oh, yeah. So you can ask questions. I think this one is turned on. Yeah. Questions. You can go ahead for the questions. But I would request Professor Ambika to give him the memento. Yeah, you are an integral part of us. Here. Okay, so questions.
Very nice talk. Thank you. So, among various the contributions for various uncertainties which you were talking field or the feedback, etc., is metallicity plays a role there, or is there a that in the modeling?
Oh, metallicity plays a huge role.
Right.
I'll tell you how it plays a role just to give you a flavor of it. So in the Romulus simulations, black holes, one of the models for black holes is if I have a cloud and it's collapsing, if there are no metals or very amount of metals, then the cloud will tend to collapse monolithically and potentially form a single black hole. So if you want to form a supermassive black hole to start with, this would be the best way to do it at this point in time. If I had then what happens is as I collapse the cloud, different parts of it will cool fast. So metals are actually coolants. So they'll cool faster and you get fragmentation. Fragmentation, you get stars rather than black holes. In fact, it's very similar to the kind of physics you think about, whether you form small mass stars or massive stars. Metal is the same way. Next, when I talk about the clusters of galaxies, and we know that the halo of clusters of galaxies are filled with hot X-ray emitting gas, there are metals that have been ejected from the galaxies. You know, those outflows are driving metals that the stars have produced into the circumgalactic medium, into the intra-group medium and the intra-cluster medium. There, they also act like coolants. And so that gas can radiate and there be a flow of gas coming back into the galaxy, which, you know, historic people have called the cooling flows. So you can also get that. And then I didn't show you this in the morning, I showed you those thermal instability and clouds forming. Those local fluctuations are also driven by cooling, and metals play a critical role in that.
Okay. So, in addition, do you give a change in the metallicity, or how do you
Yes.
deal with it? Okay.
So actually have a model that looks at metal enrichment as a function of we used to do something very ad hoc to begin with, where the yields, you know, I mean, we know that our earlier models had yields that were uncertain by factors of even the number of elements we were modeling were barely like 5. You know, it was a quick and dirty kind of calculation. But in the last 3 years, we have improved that. In fact, a graduate student that I was co-supervising, who's based in South Africa, developed the actual model, the subgrid model that does the metallicity. It's Yaki Kobayashi's chemical evolution. So we basically now have a chemical evolution model in the simulations that is more realistic. And as a result of that, we can see differences. So you know the model I showed you about how well it does with the galaxy stellar mass function? That was the post model. model actually had a little gap here and there. So things have changed in that model just came into play. So, and as we improve both the metals, the problem with metals that we have outstanding is that a lot of these don't do diffusion of metals correctly. So we're looking at developing model how turbulence will move the metals around and spread it out. And so we're trying to understand that, because that also will make a difference in terms of where the black holes form and things like that.
Thank you for the very interesting talk.